Let me now show you that the VC dimension of the optimal hyperplane, the fattest hyperplane, can be smaller than the VC dimension of thin hyperplanes. Now, this is getting more towards a theoretical justification of the fattest hyperplane, which will then mean that if its VC dimension is smaller, the link from E in to E out is going to be better. Okay, so let's erase this. Let's consider the points, the pictures on the top there. Okay, so I'm showing in 2 dimensions 3 data points. Okay, and in particular, I'm showing 4 dichotomies on these 3 data points, and the perceptron can separate all 4. In fact, we know that the perceptron can separate all 8, and we can see that, if we flip the dichotomy, if we flip each +1 and -1 point, so flip the blue and the red, you get the other 4 dichotomies. Okay. And the same perceptrons will separate those other 4 dichotomies by just, flipping which side of the perceptron is +1 and which side is -1. Okay. So you can take that top picture as illustrating that, the perceptron can shatter 3 points. Okay. But now that's a thin perceptron. Okay. You can think of that line as a perceptron, as a separating hyperplane of width 0. So now let's consider the situation where I'm going to require you to fit the data with a thick hyperplane. So imagine that I don't give you this thin hyperplane, I give you a plank of wood with some width. Okay. I'll give you a plank of wood with some width. Okay, and the width of this plank of wood is gamma. Okay. And now you take this plank of wood to your data points and you try to separate. Okay, try to separate. In particular, let's focus on that last collection of points. Okay, so I have a data point here, a data point here, and a blue point, somewhere here. Okay. A blue point somewhere here. Now, if I look at the fattest separating hyperplane for this data, it's going to look something like this. It's going to look something like this. Some margin. And it should be clear that if I'm required to separate this data with a plank of width larger than that fattest possible, it's not going to be possible. Okay, and this is what we're showing in the bottom, set of 4 pictures. So if I consider a fat hyperplane given by that sort of yellowish thickness region, so I'm considering hyperplanes that have to be at least that thick or that thick. Okay, so the first 2 dichotomies can be separated, but then the remaining 2 cannot, because if I now try to place my fat hyperplane on to separate this data, its margin extends outside these 2 points, and we require that the data points be on either side of my fat separator. So this is an example where the thick hyperplane cannot separate those 4 dichotomies. But then you'll say to me, but this notion of VC dimension and the maximum number of dichotomies allows me to place the points wherever I want. So it's an easy fix to allow me to separate all the dichotomies, to implement all the dichotomies, to shatter a set of 3 data points by just moving the data points further apart. Okay, solution. Move data points further apart. Okay, that's a solution to allow now the thick hyperplane, to allow now the thick plank to separate the data, and so that suggests that 3 data points can be shattered. Okay, and so this notion that the fat separating hyperplanes cannot separate all the dichotomies is only going to come into effect if you are not allowed to move the data further apart. So if your input space is bounded. Okay, so fat hyperplanes cannot implement all dichotomies if you cannot move the data far apart. So what matters is how far apart can you move the data with respect to the thickness of the hyperplane you're considering. So fat hyperplanes cannot implement all dichotomies if you cannot implement all the dichotomies if the data must be close together. For example, imagine that your input space is a bounded sphere of radius r. So the data is bounded within a sphere of radius r. So for example, data is bounded within a sphere of radius Okay. In which case we expect that, you know, the ratio of the radius of the data to the thickness of the hyperplane is going to play a role. So R over gamma is sort of the dimensionless parameter that's going to play a role. And indeed, theorem. So what's the VC dimension related to? The VC dimension is related to the maximum number of data points that you can shatter. Indeed, we can show that the VC dimension, dVC, i.e. the maximum number of data points that you can shatter, is less than or equal to basically this ratio squared, the sort of width, the bound on the sphere that contains the radius, so the bound, the width of the data, R, divided by gamma, the thickness of the hyperplane, squared. Okay. Plus 1. So the VC dimension is at most that. So in other words, if your data is bounded within a sphere of radius R, okay, and the thickness of your hyperplanes is now getting larger and larger. For example, if your thickness is bigger than R, then you basically can't separate anything. You can just implement two dichotomies, okay, which is plus 1 and minus 1. Okay, plus 1, you're on one side, minus 1, you're on the other side. If you put two data points, they are not separated by a distance of R, so you cannot implement the plus-minus dichotomy. Okay? And so this theorem says that if your data is bounded, then the thick hyperplanes can have a lower VC dimension, gives you a better link from E in to E out. And this is the intuition. Now, of course, we also know that, you know, the VC dimension for hyperplanes, even if they have zero thickness, is at most D plus 1. So you can certainly take the minimum of these. So the VC dimension is at most the min of D plus 1 and D min of D and R squared over gamma squared, you know, plus 1. So this is the theorem. And what this says is that if you have fat enough hyperplanes and your data is bounded, then your VC dimension can be very small. And observe that in that case, when your data dimension starts getting, your data is bounded and by a smaller and smaller radius, then the fatter and fatter hyperplanes can have a VC dimension that's approaching a constant independent of the dimension. Okay. So this suggests that it's possible with fat hyperplanes to get generalization even in large dimensions. Okay. Now, so this is so this has now moved towards some theoretical justification for the fat hyperplane. Okay. Now let's prove the result that's going to be of most practical use, which is to link sort of the optimal hyperplane to the cross-validation error. And it turns out that those support vectors, the vectors that, you know, define the fatness of the hyperplane, are going to play an important role. So let's erase and talk about the fat or the optimal hyperplane, the maximum margin hyperplane, and the cross-validation error.